This tutorial covers properties of aqueous solutions. In any aqueous solution, water is crashing into other water molecules. Thus, water is reacting with itself to some degree. One of the water molecules will donate an H+ ion, or a proton, to another water molecule as a result of the collision, and thus form hydronium ion, H3O+. So water is acting in an amphiprotic manner with itself. One of the water molecules is an acid forming its conjugate base. In this case, the proton donor is the acid, and it's going to form hydroxide. The other is the H+ acceptor, therefore, by definition, it is a Bronsted base, and it forms its conjugate acid, hydronium ion. This auto-ionization of water reaction is always occurring simultaneously no matter what else is in that aqueous solution, be it a salt, an acid, or a base. The equilibrium constant expression for this reaction of water with water is usually given the subscript W. So K of water is products over the reactants. It's the concentration of hydronium to the first power as seen with the coefficient 1 in the balanced equation, times the concentration of hydroxide. Again, both of these concentrations are at equilibrium for the K expression. At 298 Kelvin, or 25 Celsius, in any aqueous solution, no matter what's in there, the product of these two concentrations is measured to be to three significant figures 1.00 times 10 to the minus 14. So as you can see, there's very, very little ionization going on of water in any aqueous solution, which is why water is classified as a non-electrolyte by itself. This is not surprising because water has strong covalent bonds between the O and the H atoms. As seen in the reaction, for every two water molecules that react, one hydronium cation is formed and one hydroxide ion is formed. So in just a water solution, not an aqueous solution of some other substance, the concentration of hydronium at equilibrium will be some value x, as will the concentration of hydroxide. They form in a 1-to-1 ratio. So we can determine the value of each of those concentrations just by plugging x into the equilibrium constant expression for water at 298 Kelvin, and when you solve for x, you get 10 to the minus 7 molar. So the concentration of the hydronium cation and the hydroxide anion in just pure water is very, very low. At room temperature, it's 1/10,000,000th molar. On the other hand, in any acidic solution, there will be relatively a greater concentration of hydronium cations than hydroxide anions. So for example, if in an acidic solution the concentration of hydronium at equilibrium is, let's say, 10 to the minus 3 molar, then the concentration of hydroxide you could figure out just by writing the equilibrium constant expression for water, because these are aqueous solutions, and plugging in the given value. So this kW equals 10 to the minus 14, and that equals the concentration of the hydronium cation in molarity times the concentration of hydroxide anion. Again, that's at equilibrium, and that would yield a concentration of hydroxide anion of 10 to the minus 11. 1.00 times 10 to the minus 11 times 1.00 times 10 to the minus 3 gives you the kW of water, 1.00 times 10 to the minus 14. So basically, the greater the concentration of the hydronium cation in aqueous solution, the lower the concentration of hydroxide anion in that same solution, and vice versa. Now we'll talk about what happens when any weak acid, HA, or weak conjugate base, A-, or both, are in an aqueous solution. So here would be the reaction between the acid HA. Remember, Bronsted acids are H plus donors. So when the H plus cation is donated to H2O, hydronium ion is formed, and the conjugate base of HA, which is A-, forms. We can write the Ka expression for that, products over reactants. So we have A-, H3O plus, either order that can be written, over HA, which is aqueous. The water is a liquid, so that is not included in the expression. And for the equilibrium constant for the conjugate base, A-, remember bases are H plus acceptors, so this base, A-, will accept an H plus from water and form its conjugate acid HA. So we write the expression. Numerator contains the products in either order to their coefficients in the reaction over the reactants. And water is left out because it's a liquid, and A- has a coefficient of 1, which is the exponent. When you add up those two equations, the HA and the A- cancel out. And you get the reaction which is the same as the auto-ionization of water, two waters forming one hydronium and one hydroxide. We already know that at 298 Kelvin, not only the expression, but we know the value of that expression. 2 sig figs would be 1.0 times 10 to the minus 14. And we can write the expression for that as such here. We know we can get the net equilibrium constant from adding these two reactions together just by multiplying their respective equilibrium constants. So that means when we multiply the equilibrium constant expression or value for the acid times the equilibrium constant expression or value for the base, we get the net equilibrium constant for the reaction, which, as you see above, is just Kw. We could show that this is true from the expressions. I multiply Ka, which is A-, H3O plus, over HA, times Kb, HA, OH minus, over A minus, and the HA's cancel, the A minus cancel, and you get Kw. So that is a mathematical relationship for any acid and its conjugate base in aqueous solution. If you know the Ka value at a given temperature of the acid, you automatically know the Kb value of its conjugate base, because these two values must multiply to be 1.0 times 10 to the minus 14 at 298 Kelvin. And that's generally the temperature that will be used or given for these reactions. So I'll just assume that temperature from here on in. So for example, you know you have a weak acid with a Ka value of 5 times 10 to the minus 6. You know that it will multiply by the Kb of its conjugate base, A minus, would have to be 2 times 10 to the minus 9, such that you get 5 times 2 is 10, 10 to the minus 6 times 10 to the minus 9 is 10 to the minus 15, and don't be fooled, 10 times 10 to the minus 15 is 1 times 10 to the minus 14, or the Kw of water. Now we're going to look at Ka values, and just looking at the value, getting an approximation or an idea of what the percent of ionization of that acid would be in aqueous solution by having the acid HA react with water. So we can write the reaction of the acid being, again, by definition, the H plus donor, donates an H plus to water, thus forming hydronium ion and the conjugate base of the acid, A-. We write the expression, products over reactants to their coefficients at equilibrium. If the Ka value is large, then the numerator, which is the A- anion and H3O plus cation, will be in relatively great concentration, and the denominator, the unionized acid, will be in a relatively low concentration. So you know there are 6 strong acids, for example HCl. Practically speaking, at equilibrium, about 100% of the HCl molecules have reacted with water, fully ionized water, turning it into hydronium cation, and thus the conjugate base of hydrochloric acid, which is chloride, is formed, and it's such a incredibly weak base it doesn't react with H3O plus to any degree to regenerate the strong acid HCl. If it did so, we wouldn't call HCl a strong acid. So at equilibrium, when we measure these concentrations and we plug into the equilibrium constant expression, we just get a very large number, usually a value greater than 10. So this Ka of HCl, the expression would just be H3O plus, which is typically written before the conjugate base is written, but again you could write either order. When you measure those concentrations at equilibrium, you're going to get a relatively large value. For a weak acid, such as hydrofluoric acid, at equilibrium, roughly 3% of the molecules for most initial concentrations of hydrofluoric acid will react with water net and ionize and form fluoride and hydronium ion. So we'll have relatively low concentrations of fluoride and hydronium cation at equilibrium, and at 298 Kelvin the product of those ions in the expression, which would just be KaHF, products over reactants to their coefficients, H3O plus times fluoride divided by HF. Since at equilibrium most of the HF is unionized, it would be a relatively larger concentration of HF compared to fluoride, and we get a number on the order of 1 in 10,000, so that indicates a weak acid. How weak is the base fluoride? Well, if we write the reaction of the conjugate base of the weak acid, HF, that conjugate base is fluoride. In a given aqueous solution, the fluoride doesn't have to come from hydrofluoric acid. It could come from a soluble salt such as sodium fluoride. Either way, the fluoride is going to do what bases do. It accepts H+, in this case from water, and it regenerates HF, its conjugate acid. So we can write the equilibrium constant expression for that reaction of that Bronsted base, and it's again products of reactants to their coefficients. You might think because HF is such a weak acid that fluoride might be somewhat of a strong base, but as you could see from the empirical measurements that fluoride is an unbelievably weak base. It has a K value of on the order of 10 to the minus 11. So there's very, very little ionization of water coming from the fluoride. Still, relatively speaking, the fluoride anion is a much stronger base than the chloride anion. Chloride is the conjugate base of an actual strong acid. Chloride is so weak a base that it's basically not a base. It's a base in name only, just by definition. So fluoride is, relatively speaking, much stronger than chloride as a base, but in an absolute sense, fluoride is a weak base and hydrofluoric acid is a weak acid. So you can have a weak acid and its conjugate also classified as weak. In fact, that is usually the case. In general, the stronger the acid, the better it is at donating an H+, the weaker the conjugate base of that strong acid would be. For example, if you see hydrofluoric acid, it's generally a weak acid, but it has a Ka value of around 1 in 10,000, 7.0 times 10 to the minus 4. Its conjugate base will also be weak, but you could see by using the Kw calculation that Ka times Kb equals 10 to the minus 14, that its conjugate base is even weaker as a base. It is very poor at accepting H pluses from water. It's poorer at accepting H pluses from water than HF is donating. HF is at donating H pluses to water, and you could just tell that from the relative K values. The only time a weak acid and its conjugate base will have comparable strengths is when they're on the order of about 10 to the minus 7 each. You know that there are typically 6 strong acids that we've discussed all year. For bases, hydroxide is practically the strongest base that you'll find in solution, and we find hydroxide in solution from any of the 8 soluble hydroxide bases. We can infer, though, that the conjugate base of a very, very weak acid would be appreciably stronger, even if it's weak overall. So if you had a very weak acid, HA, then we would have a relatively stronger weak base, which would be A minus, and A minus would react more appreciably with water to form its conjugate acid HA and generate hydroxide. So one extreme example, we are not used to seeing ammonia act as an acid. It generally reacts with water to generate hydroxide. But just as an esoteric extreme example, if ammonia is acting as an acid, it would generate its conjugate base NH2 minus. And NH2 minus is an absolutely and even relatively very strong base. As a base, it could react with water. This is known as the amide anion, and that would react with water as a base, a strong base, meaning it would accept an H plus from water. So that would regenerate this is probably the only time I'll be calling ammonia an acid, regenerate its conjugate acid ammonia and generate hydroxide. So amide solutions will generate hydroxide and raise the pH, as you'll see, or lower the pOH of the solution.